Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to this channel Chandan Physics. In this video, we are going to discuss classical Langevin theory of paramagnetism. Let's begin. A magnetic dipole is developed within that atom due to its orbital as well as spin motion of electrons around the nucleus. The orbital and spin motion of electrons around the nucleus of an atom give rise to magnetic dipole moment. In case of paramagnetic substance, each atom has a permanent magnetic moment. How? In the previous video lecture, we understand how Langevin theory of diamagnetism is helpful to know the property of diamagnetism, as if there will be even number of electrons in the outermost shell of that given diamagnetic substances. But in case of paramagnetic substances, the outermost shell has odd number of electrons. In diamagnetic case, there will be the presence of even number of electrons, so their net magnetic dipole moment are cancelled out each other and it will be 0. But in case of paramagnetic substance, it has odd number of electrons, therefore the net magnetic dipole moment is not cancelled out, or we can say there will be no such result of 0. Therefore, that atom has a permanent magnetic moment. But these magnetic moments are randomly oriented in the absence of external magnetic field. When we apply the external magnetic field, then it will be 0. The net magnetic moment is 0 when external magnetic field is applied, and these permanent magnetic dipoles align parallel to that of applied magnetic field. In this way, Langevin theory is helpful to us to show how the substances are under paramagnetism. Let me mathematically show various kinds of properties like intensity of magnetization, susceptibility, and so on. Consider unit volume of a paramagnetic sample having n number of atoms. If mu m, that is the magnetic dipole moment of each dipole, each dipole, each atom is treated like a magnetic dipole, and theta, that is the angle between B vector and mu m vector. If that is the applied magnetic field, the magnetic dipole moment, angle in between these two are theta. It executes a torque. The torque acting on that of dipole, therefore torque acting on the dipole is tau is equal to mu m cross B vector, or tau is equal to mu m B sin theta. Let equation number 1. A small work done by that of external agency in displacing to a small angle, let d theta. The small amount of work is done by external agency in displacing the dipole through an small angle d theta. That is small work done dw is equal to tau d theta, or dw is equal to value of tau as mu m b sin theta d theta. Therefore, the total work done in displacing the dipole from 0 to theta is given by dw, total work done w is equal to integration over dw is equal to mu m b sin theta d theta. Theta change from 0 to theta, 0 to theta is equal to mu m b integration over sin theta d theta from 0 to theta is equal to integration of sin theta as cos theta as minus cos theta, and using that limits minus mu m b cos theta. That is the total work done w. But this total work done is nothing but, that is the magnetic potential energy. This total work done is stored in the form of magnetic potential energy U, and that magnetic potential energy U is equal to W, that is minus mu m B cos theta. That is equation number 2. According to Maxwell-Boltzmann's law, the number of dipoles per unit volume within a solid angle d omega and whose energy is U is the number of dipoles per unit volume within that of solid having solid angle d omega and its energy is U is given as dN is equal to A e to the power minus U by kt d omega. Equation number 3, where A, that is the constant of proportionality, T, absolute temperature, K, that is the Boltzmann's constant, d omega, that is the solid angle subtended by let me figure out it. What is d omega? Look at that figure, that is the applied magnetic field and which one is the magnetic dipole moment. If we can figure out it, that is applied magnetic field and origin O, that creates angle theta. This portion is d theta, here is let r, that portion as r sin theta, and this thickness portion, that is r smaller d theta. So d omega is the solid angle subtended by the shaded region at origin. The shaded region, how much angle subtend at origin, that is d omega. Now d omega is calculated. Therefore, d omega is equal to area of ring between theta and theta plus d theta divided by r square, or d omega is equal to area of the ring between theta plus d theta, that is 2 pi r sin theta r d theta, this portion r sin theta, that portion r d theta, that be the radius. So 2 pi r, the total area, divided by r square cancelled out, d omega is equal to 2 pi sin theta d theta. Let that d omega value is put to that of equation number 3. Therefore, equation 3 becomes dn is equal to a into 2 pi sin theta e to the power minus u by kt d theta is equal to rearranging the terms as 2 pi a e to the power minus u by kt sin theta d theta. Let 2 pi a is equal to c, e to the power in place of u we substitute its value as minus um b cos theta, minus minus plus mu m b cos theta divided by kt sin theta d theta, where we put c is equal to 2 pi a is equal to, again we substitute x is equal to mu m b divided by kt. Therefore, it will be c e to the power x cos theta sin theta d theta, that for dn. The equation number 4. So mu m cos theta, that is the dipole moment in the direction of magnetic field, mu m cos theta. The component of dipole moment in the direction of magnetic field, applied magnetic field, is equal to mu m cos theta. Therefore, the total magnetic moment per unit volume is given by total magnetic moment per unit volume is given by, that is dPm, total magnetic moment, is equal to dN, that is the number of dipoles per unit volume within that of solid angle, d omega, that is dN, into that term mu m cos theta, the component of dipole moment along that of magnetic field direction. Let me put these values. The value of dN is put here, c e to the power x cos theta sin theta d theta, c e to the power x cos theta sin theta d theta into mu m cos theta is equal to c e to the power x cos theta mu m sin theta cos theta d theta, that for dPm. Then the net dipole moment of all the dipoles per unit volume, just integrating that one. Therefore, net dipole moment of all the dipoles per unit volume is given by, so Pm, net dipole moment of all the dipoles per unit volume, that is integration from c e to the power x cos theta mu m sin theta cos theta d theta, limit from 0 to pi. Equation number 5th. Since all the orientations are within that of range 0 to pi, as all the orientations are confined between 0 to pi, hence total number of atoms in that of sample, sample of paramagnetic substance, in that sample are n is equal to 0 to n, 0 to pi of dn, total number of atoms in that of sample, integrating that one, which n is equal to 0 to pi, the value of dn, c e to the power x cos theta sin theta d theta, that equation number 6. Therefore, the average dipole moment per unit atom in that of direction of magnetic field can be calculated. Therefore, average dipole moment per unit atom in the direction of magnetic field is average mu m bar is equal to Pm divided by n. What is Pm? Pm is the net dipole moment of all the dipoles per unit volume. Here n is the total number of atoms in that of sample. Let me put these two values Pm and n are put here, or mu m bar is equal to, that is integration from 0 to pi c e to the power x cos theta mu m sin theta cos theta d theta divided by integration from 0 to pi c e to the power x cos theta sin theta d theta is equal to c mu m constant to that of outside, then integration over 0 to pi e to the power x cos theta sin theta cos theta d theta whole divided by constant c outside, integration over 0 to pi e to the power x cos theta sin theta d theta. Here c cancelled out, we have mu m integration over 0 to pi e to the power x cos theta sin theta cos theta d theta divided by integration over 0 to pi e to the power x cos theta sin theta d theta. To solve that kind of integration, we have to put cos theta is equal to u, then differentiating it, we have minus sin theta d theta is equal to du, then the limit ultimately changed. First, when theta is equal to 0 degree, when theta is equal to 0 degree, put theta is equal to 0 degree, so u is equal to cos 0 degree, cos 0 degree 1, then u is equal to cos theta is equal to cos 0 degree is equal to 1, theta 0, that value will be 1, and when theta is equal to pi, then cos pi, that is minus 1, u is equal to cos pi is equal to minus 1. So the limit change from 1 to minus 1 is equal to here 0, that is 1 to minus 1, mu m integration from, as substituting cos theta as u minus sin theta d theta, so negative sign minus 1 to minus 1 u e to the power x u du divided by minus integration over 1 to minus 1 e to the power x u du, minus minus cancelled out, then mu m integration over 1 to minus 1 u e to the power x u du divided by integration over 1 to minus 1 e to the power x u du. That integral can be solved. So mu m, that integral can be solved by using integration by parts method. We just use it directly as 1 by x e to the power x plus e to the power minus x minus 1 by x square e to the power x minus e to the power minus x divided by, again its integral is evaluated 1 by x e to the power x minus e to the power minus x is equal to mu m, that exponential e to the power x plus e to the power minus x is nothing but in terms of hypertrigonometry function, that is cos hx divided by x minus here e to the power x minus e to the power minus x, that is sin hypertrigonometry function sin hx divided by x square whole divided by, again e to the power x minus e to the power minus x, that is sin hx divided by x. When that term is multiplied to this, so mu m cos hx by x minus sin hx by x square whole into x divided by sin hx, we obtain mu m, that multiplied by this term x is cancelled out, cos hx divided by sin hx minus 1x cancel out, sin hx cancel out, so 1 by x cos hx divided by sin hx, that is cot hx minus 1 by x, that is the value of mu m bar. Now intensity of magnetization is calculated. Next, the intensity of magnetization produced in that given sample. Intensity of magnetization I is equal to total number of atoms in that of sample into that average dipole moment per unit volume. So that is the average dipole moment per unit volume of the atom. Or I is equal to n mu m cot hx minus 1 by x, as we derived um bar, that much. Or I is equal to n mu m cot hx 1 by x, that is L of x, where L of x is equal to cot hx minus 1 by x, that is called Langevin function. Langevin function, intensity of magnetization. Two cases we have to discuss. Case number 1, when mu m into b, that is very greater than that of kt, then what happened, the value of x, as we put mu m b divided by kt, that is much greater than 1, means x is very large, that is x is very large. In this case, either t is small or b is large, then we achieve x is very large. In this case, either t is small or b is large, then the Langevin's function L of x at x tends to infinity, x is at very large, so cot hx minus 1 by x at x tends to infinity is evaluated. Cot hx function e to the power x plus e to the power minus x divided by e to the power x minus e to the power minus x minus 1 by x at x at infinity is equal to e to the power x in that of numerator side taking common, and also e to the power x in that of denominator side taking common, and these two are cancelled out. So, we obtain 1 plus e to the power minus 2x divided by 1 minus e to the power minus 2x minus 1 by x, x tends to infinity. Now, evaluate at x tends to infinity, that is 1 plus 0 divided by 1 minus 0 minus 0, finally that result will be 1. So, the Langevin's function at x is equal to infinity is equal to 1. Therefore, when we put it that value at that of particular expression, so we obtain, let it be taken as equation number here equation number 7, equation number 8. Therefore, equation number 8 becomes I is equal to n mu m, or I is equal to that is I of s is the saturation value of the intensity of magnetization. That is n mu m as is where is, that is n mu m, which one is the saturation value of intensity of magnetization, So, what we obtain from that of particular expression, this is the condition where we show when all the dipoles are completely aligned in the field direction. When all the dipoles are completely aligned in the field direction. Therefore, at that of condition we obtain total saturation value of that of intensity of magnetization. Case number 1. Next, at case number 2, if that term is very less than kT, then what obtain? Case number 2, when mu mb is very less than kT, then x is equal to mu mb divided by kT, which is very less than 1. At that of condition, that is x is very small. In this case, either t is large or b is small, just opposite of case number 1. Then the Langevin function L of x can be approximated as, so L of x is nearly equal to cot hx minus 1 by x, expanding cot hx is 1 by x plus x by 3. Like another terms, the higher terms are neglected, minus 1 by x therefore we obtain 1 plus x minus 1 minus x, that is x by 3, x as mu m b divided by 3 k t. Now, the equation number 8 becomes, therefore, equation 8 becomes intensity of magnetization I will be n mu m square b divided by 3 k t. For paramagnetic material, intensity of magnetization is very large, is very small. Therefore, magnetic field B is equal to mu naught H plus I, that is nearly equal to, since it is very small, we neglect that intensity of magnetization, so it will be mu naught H. Putting that value, in case of B, we obtain, putting this value, we get I is equal to n mu m square mu naught H divided by 3 k t. And the magnetic of susceptibility of that paramagnetic material, and magnetic susceptibility of paramagnetic material is xi m is equal to I by h intensity of magnetization divided by h is cancelled out. So, it will be n mu m square mu naught divided by 3 kT. Therefore, chi m is equal to C dash divided by T, where C dash is equal to n mu naught mu m square divided by 3k is known as Curie's constant. Therefore, we say that x chi m is inversely proportional to 1 by temperature. That equation shows that magnetic susceptibility of paramagnetic material is positive, and varies inversely as absolute temperature. And this is nothing but Curie's law. Magnetic susceptibility of paramagnetic material is positive and varies inversely to that of absolute temperature. This is known as the Curie's law. So, here we show mathematically it as how mathematically derived. First, taking magnetic field to that of magnetic dipole moment, then the torque, work done, total work done is nothing but the potential energy. According to Maxwell-Boltzmann's law, number of dipoles per unit volume within that of solid angle d omega, number of dipoles per unit volume dn, then d omega is evaluated and that value is putted, and finally we obtain the total magnetic moment per unit volume, that is the net dipole moment of all dipoles for that unit volume, and finally the average dipole moment per unit volume of that of atom in the direction of magnetic field mu m bar, that is Pm divided by n. Next, intensity of magnetization is calculated. Two cases when that is very greater than kT, we obtain the saturation value of intensity of magnetization, and when it will be less than that of kT, very less than that of kT, we obtain the intensity of magnetization and susceptibility of the paramagnetic materials. So, with the help of this video lecture, we understand the concept of classical Langevin theory of paramagnetism. And mathematically show the intensity of magnetization during two cases, and also the magnetic susceptibility. So, with this useful and informative notes, let me wind up this session. Thank you.